Any questions, first of all, about the laboratory? We got that in. I think I'm not going to grade that until Sunday. So if you still don't have it in, that's okay. There were people absent. Hopefully they got that taken care of and figured out what they needed. But good. All right then. Let's open up to page 22 and take a look at this. So, you guys know how the planets work, right? We have this gravitational pull of all of these different planets and the moons in the solar system and the universe, everything going around everything else. If we take a look, if we look at a bond between two atoms, basically that is sharing of electrons, right? And these electrons, you know, this is just the highest probable place for them to be. We call that an orbital. This may be for, if it were hydrogen, these would be both in the s orbital for the hydrogen. If this were something like carbon and hydrogen, then it would be in what we call the sp3 hybridized orbital. So basically we know that if a hydrogens, their spheres will overlap, right? And we will have those two electrons in that overlapping part. Carbon, we have the S and the P orbitals. And basically we know we have one electron in each of those because carbon has 4 valence electrons. But this happens with everybody that has an S and P, oxygen and all of these different ones. If you have that tetrahedral arrangement, instead of these spheres and instead of these dumbbells, basically they form what's known as an sp3 hybridized orbital. So basically they come out in those 109.5 degree angles. And then if these were H's, the sphere of the s orbital of the H would kind of overlap with that sp3 hybridized orbital. Or if this were fluorine, then fluorine's the hybridization of fluorine would then overlap that as well. It's kind of cool. You can basically count S, P1, P2, P3. If you have 4 locations for electrons to be, then it's called sp3. That's basically the tetrahedral electron arrangement. Keep in mind that that's not just the shape, that's the arrangement of the electrons. If you have, let's say, this right here, you don't count the double bond as 2 bonds, you count it as 1 location for a high density of electrons. So here you have sp2 hybridization. 1, 2, 3, sp2 hybridization. If you were to have carbon dioxide, and I know I'm not being fair to the valence electrons, but if you were to have carbon dioxide, you would have sp hybridization. So basically these orbitals act as 2 locations for sp hybridization. sp2, you have 1s and 2p orbitals hybridizing to act as 3 locations for the electrons to be heavy in. For 4, the tetrahedral arrangement, you've got sp1, 2, 3 of 4 orbitals. With this one, sp2 is trigonal planar. Right? And what if we had something that was a nice seesaw? Then we have 5 locations for electrons to be. So this would be sp3, we know will give us 4. D1. This has to occur 3rd period or higher. So like phosphorus would be able to do this. And then if we went sp3d2, that would be octahedral. And that could also be 3rd period or higher. So to get this into your brain, the easiest way to do it is to remember that orbitals are just spaces around atoms where electrons can be. Whenever you have a bond between 2 atoms, they are basically sharing electrons. Now they are sharing electrons. What that means is those electrons are basically somewhere between them, and they would be in what we would call an sp3 hybridized orbital. Or if it were this, they would be being shared within an sp3d1 hybridized orbital. And that's the basic of it. So we know that the charge of the nuclei are positive, and we know that the charge of the electrons are negative. So if we look at the energy for a bond, if we took these and tried to squeeze these 2 things closer together, they would repel. So that would not be energetically favorable. If we tried to pull these apart, then maybe the positive nucleus could not attract the negative electrons. So what there is if we look at energy over here and we look at distance or radii, which we've already discussed, atomic radii, right here, we will actually find that the shorter the radii, we actually require energy to push them this close. So you'd have to actually put energy in. You can see I've got energy as being 0 here. There is a certain point, and that's that lowest point. That distance right there is where that bond is basically at its optimal. And here the energy is negative. This would be the amount of energy we would need to put in, if you remember endothermic versus exothermic. If the energy is negative, this is the amount of energy we would have to put in there in order to start to separate that bond, to break that bond. That energy right there, that's the bond energy, is also called bond dissociation energy, which means that we are able to break that bond. In order for things to occur, you take the bonds broken and you subtract the energy of the bonds formed. This would be the summation of these. That will give you the delta. What do we want to call it? Let's call it delta H for the reaction. A lot of times this gets confusing because you guys just came out of bio, probably, or you had bio recently. They always say that bonds are stored, energy is stored in bonds. That's not true. It takes energy to break bonds. We can see that from this diagram. This is the amount of energy to break this bond. We've got to put that amount of energy into it. Now, if that bond, if a bond reforms with that atom or that group, then it may take less energy, which would mean we would have a surplus of energy being given off. That would be an exothermic reaction. If it took more, if we had to put more energy, then obviously it would be an endothermic reaction. So the concept and ideas behind this is very hard, but the math problem is pretty easy. First off, You got to be able to have a balanced equation. Then we got to know the form. So this is CH4. So how many CH bonds do I have there? I have 1 mole of CH4. How many CH bonds do I have there? Easiest question of the day. Okay, let's count them.
4.
Yeah, right. Easiest question of the day. 1, 2, 3, 4. So then I have this group of bond energies in kilojoules per mole. I have 4 CH bonds. So CH bonds 4, and they have bond energies of 411. So I need to put that energy in to break those. So 4 times 411 kilojoules. Cl, 2. So this is Cl. How many Cl-Cl bonds are in one Cl2?
Two.
There's 1 in one Cl2, but I think you were looking at the fact that we have 2 of these here. So we go down here to Cl. It takes 240 kilojoules. And I'm going to get rid of this real quick. It takes 240 kilojoules of energy per mole to break one Cl-Cl bond. So we have 2 moles of that. So 2 moles is 240. Plus, here we have F2. So it's the same case except for it's with F. F to F is 155. So we'll multiply that by 2. All of these are in kilojoules, by the way. So if we add this up, that is the sum of the bond and the energy needed to break these bonds up. Then we must subtract the energy of the bonds formed. And so if we subtract this, that will tell us the difference between the energy that we required to break it and the energy of the bonds formed, and that will tell us how much excess energy we have given off. So CF2, Cl2. Anybody tell me the bonds that we have there?
Two that are CF and 2 that are CCl.
Good. So we need to look at the CF bonds. Oh, it's going to be under F. Oh, here it is. CF 485, and it was said that we have 2 of those. Cl. NC is 327, so we have 2 of those as well. What did I say, 327? We have 2 HF bonds. $565. And 2 HCl bonds at 428. So 4 times 411 plus 2 times 240 plus 2 times 155.
The answer is 2,434.
45 times 2 plus 2 times 327 plus 2 times 565 plus 2 times 428.
That would be 2,730.
Is that right? Nope. 2 times 485 plus 2 times 327 plus 2 times 565 plus 2 times 428.
The answer is 3,610.
So this is the energy required to break the bonds. This is the energy when the bonds form. 2,434 minus 3,610.
It's negative 1,176.
So that is negative 1,176 kilojoules per mole of CH4 for this whole equation to occur. Yep. So if we had 2 moles of this, then that would give us, if you recall from our using the delta H of enthalpy, but then we could get, 2,300 some. Questions there? Math
Wait,
behind
so
it is pretty easy, right? But the
the
conceptual
energy
theory
needed
is
to
a little
break
bit difficult.
bond minus what?
Louder?
It's the energy needed to break the bond subtracted from what?
Minus the energy, the summation of the energies that the bonds formed.
Okay, thank you.
Mm-hmm. So a lot of stuff that we did with energy was we took always the products minus reactants. This is the first one where you take reactants minus products from last semester, right? So again, what type of bond's going to be here between N and 2 or N2? This is where this gets hard. What's that going to look like? What's the Lewis structure of N2 look like?
Linear?
Yes, but can you describe it more?
Is it a triple bond?
It's got a triple bond. And that's what's going to make this hard, because you look down here, here's N double bond, here's N triple bond. So we got to make sure that we understand that these are going to be closer together, and this is going to be of a higher, stronger energy because it's a triple bond. So that's 942. We only have 1 mole of that, plus 3 moles of a hydrogen double bond. And to tell you the truth, I would do this math now with your calculator just so you don't have to write a bunch. 3 times 432.
It's 1,296.
All of these are in kilojoules. And then we have to write out NH3. So that means we have 3 nitrogen hydrogen bonds, each one at 386. But we have 2 moles of that. Is that too fast? We have 3 hydrogen nitrogen bonds, each one at 386, but we have 2 moles of that. So basically we have 2 sets of 3, each one being 386. 6 times 386.
It's 2,316.
940, what is that? 942 plus 1296.
It's 2,238.
2,238 minus 2,316.
That would be negative 78.
So we get negative 78 kilojoules.
So if H is a negative, does that mean it's giving off that much heat rather than,
Yep.
so it's like warming up the, okay.
Yep. Delta H is negative, so it's giving off that much heat when we break these bonds to form this. Yep.
I have a question.
Mhm.
So for this one, since for every like one with H, do you multiply how many H's there are by how many moles there are?
Yeah, just like we did this one, we had 4 bonds. So it's the number of bonds that you have. We only had 1 mole, so we didn't have to do any multiplication there. But here we have 1, 2, 3 bonds of nitrogen and H's here, but we have 2 moles of it.
Oh, so that's why like N is like there's only 1 bond, so you only use 1.
There's 1 number because it's a triple bond,
Yeah.
but we have the reading for the triple bond.
Okay, so these numbers are for the energy for the bonds.
Yes, they are the bond
thank you.
energies. Yep. Any other questions? Then I suggest you do 3 and 4 and 5. What do you got? 20 minutes to do that. I will keep the Zoom open or whatever, but you're more than welcome to get out of here and get it done. If you want the answers to these to check if you're right, number 3 is 104. I don't have this one yet, but I'll get it for you tomorrow. But that one is negative 104. And I'll get this one tomorrow. This one, does anybody look down there real quick and see which one has the highest, strongest bond? Hudson?
I have not.
So what are you looking for? You're looking for the bond energy that's the highest? Hydrochloric, hydrobromic, hydroiodic, or hydrofluoric?
Is it hydrofluoric?
Yes. So it has the biggest number, so it would have the strongest. It would take the most energy to break that bond, right? Now let me ask you this. Notice fluoric is the highest, chloric is lower, bromic is less. Where do you think iodic would be?
What do you mean diodic?
Iodic, hydrogen iodic, or hydroiodic, HI.
Would it be even lower?
It would be even lower. Can anybody tell me why fluorine has the greatest bond energy with hydrogen and iodine has the weakest?
Does it have higher electronegativity?
You got it. As we go down in electronegativity here from fluorine to chlorine to bromine, the attraction forces is weaker, so it won't take as much energy to break that bond. Excellent. That's all I have planned for today. Very light lesson today. Tuesday's lesson will be light as well. Have a great 3-day weekend. As I said, I'll stick on here. If you have any questions or whatnot, I'll probably work through problem 4 real quick just to get that answer for you for Monday. Other than that, see you guys. Take care. Bye.
Wait, Mr. Jackson.
Mm-hmm.
So So the higher the bond energies is the higher electronization.
Well, it's the stronger the bond, and for the fluorine down here, this HF, we know the electronegativity is higher, so it's pulling on those electrons and hydrogen tighter, and that's what makes that bond energy so strong.
Oh, gotcha. Okay, that makes sense. Also, is that me?
It was
Yeah.
it was you whenever I got like 6 like right in a row, like at 9 o'clock or something. What were you doing? I can't hear you. Yeah. Try to unmute.
Okay, there we go.
There we go.
Yeah, it was like, so for PDFs, if I like do it over a long period of time, I have to keep submitting it and saving it, or otherwise I won't be able to access it and like keep working on it. So I
Oh,
have to submit it every time I add something on the PDF.
That happened to me too, Olivia. I'm pretty sure I did the same thing because I kept saving it and then it like got deleted, and so I had to ask someone else for help, and eventually I just gave up on it.
yeah.
Yeah.
It was you two, and I was just sitting here going like, "What are they even doing?" And I didn't open it or look at it or anything, but I just like my
I'm
notifications.
so sorry.
No, not at all.
Oh,
I've hidden them, but I was just funny. Like I wasn't doing anything; it was just sitting next to me. But I was sitting there like, "Wow!" But yeah. Funny.
It's because like I had the PDF and then I had another PDF for all the pictures, and I was trying to, it was like a long process, but basically every time I like add something on that PDF lab, I have to like resubmit it to save it
Huh.
so I can access it here. Yeah. It's super weird.
Super
But
weird.
I hope teachers don't get messages every time I submit something, but I guess they do because I do that for a lot of classes.
Oh, we do, but we don't mind usually, right? Yeah, it's fine, definitely. Otherwise, the teacher would just take it off their phone. They would
Yeah.
just do it. Yeah, it wouldn't be a big deal.
All right. Thank you.
Yeah, have a great weekend.
You too.
Mr. Jackson, I was just wondering, like on the lab, like it said there was, the column that said like the Lewis structure. Were we also supposed to draw the Lewis structure, or was that just supposed to be for the pictures?
Were you supposed to draw? So if you look at the lab, yeah, you were to draw the Lewis structure in the first box where it said Lewis structure.
Okay.
And
Is
then,
it okay if I resubmit? Because I just didn't do that part.
yeah, that's fine. But you have like the bond, you have the shape.
Yeah, I have everything else. I just thought that was supposed to be for like the pictures we took.
Oh, I get you. Yeah, you should have one that's drawn with all the dots on it, and then you should have one that is what do you call it? One that is the actual three-dimensional model. So one drawing.
Yeah.
Yeah.
Okay, I'll resubmit that tonight. Sorry about that.
No worries at all.
Okay, thank you.
Yep. Have a good weekend. Alexa, shuffle my playlist school songs.